As you'll remember, we discussed that all devices that are installed in a computer need specific resources in order to be able to function. These are called system resources. They include IRQs, I/O addresses, memory addresses, and DMA channels. Now these resources are sent to the devices through the system board through the bus lines and eventually make their way all the way to the expansion slots. In older PCs, we had 8-bit expansion slots, which limited the amount of resources we could send to a device. In newer PCs, we have 16-bit expansion slots, 32-bit expansion slots, and we're working towards 64-bit expansion slots. This is like taking an 8-lane highway and expanding it to a 64-lane highway. You can see what a huge difference that would be. As a matter of fact, the difference between a 16-bit expansion slot and an 8-bit expansion slot is that a 16-bit expansion slot adds 8 additional data lines, 5 additional IRQ lines, 4 more DMA channels, and 4 additional address lines. So you can see that's a huge difference. Now let's take a closer look at the resources that are sent out to each of the devices in the computer. First, let's look at IRQs. IRQs, interrupt request numbers, also called hardware interrupts, are an event caused by the hardware device signaling the CPU that it requires service. In other words, when one hardware device needs to work with software or work with another device, it has to go through the CPU in order to get that service. So it interrupts the CPU. IRQs are very specific, and we need to remember the most common IRQs. IRQ 0 is always the system timer. A way to remember that is that most clocks and watches are round, and so is the 0. So the system timer is IRQ 0. The keyboard controller is IRQ 1. Isn't the keyboard the first thing that you touch when you sit down at a computer? So the keyboard controller is IRQ 1. IRQ 2 is reserved and not used. We'll take a look at how IRQ 2 is used by the system in just a minute. IRQ 3 is an odd number, and it goes with the COM ports that are even numbers. IRQ 3 goes with COM port 2 and COM port 4. IRQ 4 is an even number, and it goes with the odd numbered COM ports. So IRQ 4 goes with COM port 1 and COM port 3. IRQ 5 in older computers was a local printer port 2. In newer computers, which are usually networked, IRQ 5 is taken by the network interface card. IRQ 6 is the floppy drive controller. There's two ways to remember this. The word floppy starts with an F, which is the 6th letter in the alphabet, and the word floppy contains 6 letters. So the floppy drive controller is IRQ 6. IRQ 7, lucky number 7, is local printer port 1. If you're lucky enough to have a printer directly attached to your computer, you don't have to get up and go get what you printed. So local printer port 1 is lucky number IRQ 7. Other IRQs that then cascade from IRQ 2 include IRQs 8 through 15. Of these, the IRQs that are most commonly available are IRQs 10 and 11. So you can see there's a lot of resources available to devices within the computer. Another resource that devices need is a memory address. A memory address is a number assigned to both ROM and to RAM so that the CPU can access that memory. When a device asks the CPU for help, the CPU has to be able to find the resources that will allow it to help that particular device. The memory address is where the CPU looks to find those resources. In the next segment of this section, we'll take a look at how memory is assigned in the most common operating systems, beginning with DOS. Okay, believe it or not, the makers of DOS, Microsoft and the other geniuses that first came up with the PC computer and the DOS operating system, had the belief at first that it would be a long time before anyone would use more than 1 megabyte of memory. And the DOS model is based on that assumption. The first 640K of that 1 megabyte of memory is called conventional memory. And this memory was to be used to house DOS and to give it plenty of room to operate. DOS took up about 64K. So they gave DOS 10 times as much space in conventional memory than it needed for itself. Then the last 384K of the first 1 megabyte of memory was called upper memory. Upper memory was where we began to learn we needed to get device drivers loaded. Because when we first started working with DOS, we found that DOS would run much faster if we kept things out of conventional memory. This led to all kinds of third-party programs that people bought in the 1980s to move DOS, or to move programs out of DOS's way. Now we use considerably more than 1 megabyte of memory, and all memory that's used in DOS and Windows 9X programs, which are still based on the DOS memory model, all memory that is above 1 megabyte of memory is called extended memory. Some principles of memory addressing are: memory is assigned during the boot process. BIOS or real mode device drivers may only work if they're given a specific group of addresses, usually the upper memory range between 640K and 1024K. And there's also a principle called shadowing, which speeds up transfer. ROM, read-only memory, is not quite as fast, or not nearly as fast, as RAM, random access memory. So to speed up processing, the first time that memory that's in ROM is needed, it's shadowed into RAM. That way, when a device needs to use that same memory again, it can be accessed much faster. Another resource that all devices need is an I/O address. An I/O address is a number used by that device and the CPU to manage the communication between the two. These are also called port addresses or I/O port. It's kind of like a frequency that's listened to by a device. And each device has its own specific address or frequency. This allows the CPU to always be able to access the device when the CPU needs to get that device's attention, either for software or for another device. Some devices also require a DMA channel. The CPU is extremely busy. Anytime we can shortcut a method whereby an input-output device can send data directly to memory without bothering the CPU, that's going to speed up processes in the computer. So a DMA channel, a direct memory access channel, is used by some devices to gain access to RAM without bothering the CPU. 8-bit data transfer in slower machines it uses DMA channels 0 through 3, the first 4 DMA channels, 0, 1, 2, and 3. Faster 16-bit data transfer uses the DMA channels 4, 5, 6, and 7. So to put it all together, to allocate system resources and use them to manage hardware devices, at startup, BIOS and the operating system work together. They assign all the hardware devices the following: an IRQ, by which it can signal the CPU that it needs attention, some I/O addresses by which the CPU and the device will communicate, some memory addresses that indicate where the program to manage the device is stored, and then perhaps a DMA channel to speed up sending data to memory without bothering the processor. So now that we've looked at the most common resources that are sent through the system board, let's take a closer look at the system board itself.